Hidden in the rugged terrain of New England are echoes of an unseen force that can grind through mountains and completely reshape the landscape. This force is in the power of ice to slowly but surely break apart solid rock. 20,000 years ago, New England and large parts of North America were covered in over 5,000 feet of ice as it was in the clutches of the last ice age. Because these ice sheets have long since retreated, the climate has warmed, and forests, farmland, roads, and cities have sprung up in their place, it's not obvious that they were here. But if you know where to look, you can see the clear evidence that these glaciers left behind. And we can travel to places where glaciers still exist, where the land is still being actively shaped by these massive bodies of ice, and which help us imagine more clearly what New England must have looked like at the end of the last ice age. A glacier is a giant body of dense ice that forms over centuries from compacted layers of snow. This occurs in places where the amount of snow that piles up year after year is greater than the amount of snow that melts and sublimates. Today, we find glaciers in polar regions and in high mountains. The glaciers in this video are from western Svalbard, a set of glacier-covered islands north of Norway. These massive moving bodies of ice have a colossal effect on the landscape. The rock underneath the glacier gets eroded on a huge scale by the glacier. Through this process, the landscape is dramatically altered. One very clear example of where glaciers have carved through the landscape in the past are U-shaped valleys. If you live in New England, New York State, the upper Midwest, or other regions where ice sheets covered the land during the last ice age, you are surrounded by landscapes shaped by glaciers. The rolling hills, valleys, and many lakes and rivers are the legacy of glacial activity. These landscapes are a testament to the incredible power of ice. If you could compare what the landscape of the area around Boston looked like, for example, before the last ice age, and what it looks like today, it would be hard to recognize that it is the same location. So, how do glaciers actually move? Over hundreds or thousands of years, as the ice builds up forming the glacier, it will begin to move downhill under the gravitational pull of its own weight. The pressure caused by the sheer weight of ice is enormous. Where there are obstacles in the bedrock, the pressure will increase enough to melt the ice in a process called regelation. If the surface of the bedrock is rougher with more obstacles, there will be more melting. Water under the ice will then lubricate the glacier and help it slide down faster. The movement of the glacier along its base is known as basal sliding. More meltwater can cause the amount of basal sliding to increase. This clip is from an amazing time-lapse video from the PBS program Nova. It was taken from underneath a glacier which was sliding over Mont Blanc in France. The researcher used a bicycle wheel pressed against the bottom of the glacier to quite literally measure how fast the glacier was sliding downhill at that position. If basal sliding was the only way that glaciers moved, then we would observe the mass of ice moving in a uniform way. But the ice itself is also flowing and deforming in a process called creep. This is the downward flow of ice crystals moving past one another. Even in glaciers completely stuck to the bedrock where no basal sliding could occur, creep can occur as the bits of ice in the glacier slide past one another. Because there is more resistance at the base of the glacier, creep generally happens more quickly closer to the surface of the glacier. But most glaciers are moving with a combination of basal sliding and creep. To get a sense of the difference between basal sliding and creep, we can use the analogy of a moving walkway at an airport. The walking movement represents the basal sliding, and the moving walkway itself would represent the creep. While the person moving without the moving walkway continues forward, the person on the moving walkway moves faster, in the same way that the top of the glacier moves faster as a result of creep. So, how do glaciers accomplish this massive transformation of landscapes? As they move, Glaciers erode rock through plucking and abrasion. When the moving glacier encounters resistance in the bedrock, regelation will occur, melting due to increased pressure. Then, after that meltwater passes over the obstacle, it will refreeze on the other side. Water can seep into cracks in the bedrock. Then, when that water refreezes, it will expand, further breaking up the rock. The refreezing of the ice on the rock can pull the rock up into the glacier. This is called plucking. These smaller rocks then get pulled into the glacier itself and move with the glacier. Glaciers incorporate so much loose rock into their mass that many parts of a glacier appear dark and dirty. In some places, close to the base or edge of a glacier, it can be extremely difficult to know where the glacier ends and the solid rock begins. All of this rough debris incorporated into the glacier now grinds against the bedrock, further scraping, scratching, and polishing the rock. This process is called abrasion. Sometimes you can see evidence of abrasion in places where glaciers have retreated. In this recently deglaciated area in Svalbard, you can see deep scratches in the rock called scarring caused by abrasion. In this image, the smaller scratches come from the abrasion of glacial rock scraping against the bedrock. The larger grooves you can see are caused by fluvial erosion, which is when meltwater under the glacier carries sediment which also carves into the rock. There are still a few places in New England where glacial scarring from the last ice age is visible, such as this rock face in the White Mountains of New Hampshire. All of this plucking and abrasion at the base of the glacier, repeated countless times over hundreds or thousands of years, can literally tear down mountains and adds enormous amounts of sediment to the glacier. Some glaciers flow all the way to the ocean and can extend a considerable distance out into the ocean water. These are known as tidewater glaciers. The edge of the glacier face shows the boundary where the glacier ice is no longer able to support itself. But since the glacier continues to flow from behind this point, ice is pushed off into the ocean and icebergs form. This process is known as calving. Where the climate is stable, the position of the glacier face will remain in more or less the same place, even as icebergs regularly calve off the face. New ice is pushed from behind to replace the lost ice. In a system where the climate is cooling, this glacier face may advance forward, further into the ocean. In a system where the climate is warming, as we see today, the glacier face will retreat backwards. This is often accompanied by increased calving of icebergs. The most recent ice age ended around 18,000 years ago. At the height of that glaciation, Boston was under 5,000 feet of ice. The effects of that amount of ice can still be seen by the landscape left behind. One example of glacial landscapes that can be seen as glaciers retreat are long, narrow hills called moraines. Moraines are massive collections of loose glacially carved rocks, which are created as the conveyor belt-like action of glaciers moves rocks forward and to their sides, leaving these very large piles of rock behind after they retreat. Beneath their surface, glaciers have intricate networks of meltwater channels and subglacial lakes. Subsurface channels carry enormous amounts of sediment and can leave behind long, snaky hills known as eskers. Glacial erratics, large boulders transported and deposited by glaciers, are often found far from their original location. These erratics tell a story of immense transport power and the vast distances glaciers can cover. By studying features such as these, and by analyzing the immense amount of sediment that glaciers leave behind, scientists can model how glaciers move and change. Understanding the past can also help inform the present and future movement of ice on planet Earth. In the past, natural factors caused the advance and retreat of ice. Today, humans are pumping carbon dioxide into the atmosphere at a rate unprecedented in the Earth's history. This is causing the atmosphere to warm quickly. Rapid warming is causing glaciers to retreat quickly, threatening ecosystems, sea levels, and freshwater supplies. These images, taken 10 years apart, show the dramatic retreat of ice in just one glacier system in Svalbard, Norway. Melting of glaciers on a similar scale is happening all over the Arctic and Antarctica, as well as in alpine glaciers in areas like the Alps and the Rocky Mountains. By taking action on climate change, hopefully we can help prevent the loss of these breathtakingly beautiful and critically important elements of our planet. So, as you wander through the beautiful regions of northern North America that many of us call home, look around for evidence of our icy past. Stop to think about how studying these clues and learning from existing glaciers near the poles can help us understand not just the past, but inform our future as well.